Welcome back. So let's start today with some examples of convex functions, and then subsequently we will also develop some properties of the convex functions. Okay, so the first example, which is actually a proposition B2 from Birdsicas, is that a linear function is convex. So let's prove it. So a linear function means f of x is equal to c transpose of x, where x is in Rn and usually c is of course also in Rn. This c is usually called as the cost vector, and this is actually a objective function in the linear programming problem. Objective function in linear programming problem. Further, usually you minimize the cost, right? So usually the linear programming is minimize C transpose X subject to Ax equal to B and X greater than or equal to 0. This is usually the most common linear programming formulation. Let's put this in a box. I think I have discussed linear programming problems in my very first earlier lecture, so you have some idea of that. Now what we are saying is that this objective function of linear programming is convex. So what should we do? We should first take two arbitrary points, x1 and x2 in Rn, and they give you cost of C transpose x1 and C transpose x2. Now take a point anywhere on the line segment joining x1 and x2. So you have this point here, which is given by lambda x1 plus 1 minus lambda x2, and the lambda comes from the closed interval 0, 1, and you have to show that this is less than or equal to lambda times of fx1 plus 1 minus lambda times of fx2. So expand this this thing, just a simple expansion, and this is C transpose of lambda x1 plus 1 minus lambda x2, which is same as lambda times C transpose x1 plus 1 minus lambda C transpose x2, which is same as lambda f of x1 plus 1 minus lambda f of x2. So what, as Sherlock Holmes would say, trivial, my dear Watson. Okay, now let's look at the next part. What does it say? A vector norm is convex. So let's write vector norm first. So what's a vector norm? Vector norm is a function which is a on a x coming from Rn. This is the vector norm. It is greater than 0 for all x not equal to 0. If you take two vectors x and y in Rn, then it meets the triangular inequality. And lastly, if you do a scalar alpha times of x, then it is same as scaling the norm by the mod of alpha. So this you recall that this is the this is your vector norm. Now we have to show that. So what we need to show, what is it? F of x is the norm of x, is it not? Now what we need to show, what we need to evaluate, f of lambda x1 plus 1 minus lambda x2, where again x1 and x2 are arbitrary functions coming from Rn. So if you look at this, this is same as the norm of lambda x1 plus 1 minus lambda of x2, and now apply triangular inequality on this. So this is less than or equal to norm of lambda x1 plus norm of 1 minus lambda times x2. And now apply the property 3. So this is same as lambda times of, but I am taking lambda from 0 to 1, so it is actually a positive quantity. And so because it is a positive quantity, I will just not write modulus of lambda, I will just write it as lambda times of x1, and same way plus 1 minus lambda times norm of x2. But norm of x1 is fx of 1, so therefore this will become equal to lambda times of this will become equal to lambda times of f of x1 plus 1 minus lambda times of f of x of 2. And what is propagating here? Triangular inequality. So therefore f of x is less than or equal to lambda times of fx1 plus 1 minus lambda times of fx2, which basically means that the function is convex. Good. So now let's look at the last no, the C part of it. What is the C part of it saying? The C part of it is saying that the C part says that the weighted sum of a convex functions with the weighted sum of convex functions with positive weights is convex. So we need to now prove this inequality. So let's write first f of x as w1 times f1 of x plus w2 times f2 of x, and so on up to wn times, let's say, or wp times, let me write this as wp times of fp of x. And what is given to me? The weighted sum of convex functions with positive weights is convex. This is what I want to prove. So what is given to me is that the weights w1, w2 and so on up to wp are all greater than 0. If it is 0, anyway it won't be inside itself, right? That so weights are all greater than 0, and f1x, f2x and so on up to fpx are convex, right? So now just look at f of x1. What is that? w1 of f1 of x1 plus w2 of f2 of x2 and so on up to wp of f1 of f2 of x1 and so on up to fp of x1. What is f of x of 2? Again weighted sum, same weighted sum, but now evaluated at x2. So it's the same weighted sum but now evaluated at x2. And where should now we to prove the convexity of this function, what we should do? We should now evaluate it at an intermediate point on the line segment from x1 to x2. And so I'll just use the sigma notation now. So wi fi of lambda times of x1 plus 1 minus lambda times of x2. But each of these fi's being convex, I can induce the property of convexity and write this as wi of fi, I'm sorry, 1 minute, wi of, open a bracket first, wi of Now, what is fi of whatever is here is less than or equal to lambda times of fi x1 plus 1 minus lambda times of fi of x2. So that's what I am going to plug it in here. So that's what I am going to plug it in here, and so uh, so what do I get now? I get this, and now I expand it further. I expand it uh, for further and write this as I equal to 1 to p summation I equal to 1 to p lambda times, I'm sorry, see this playing of symbols, you should do it comfortably, all right. Try to pick up that habit of playing with symbols comfortably. I will now write it as lambda times of sigma I equal to 1 to p wi fi x1 plus common factor 1 minus lambda in the second term taken out, and then summation of I equal to 1 to p wi fi of x2. And but what is this? What is this term here? This is f of x1. So lambda times f of x1 plus 1 minus lambda times f of x2. And what has been induced on f of this lambda x1 plus 1 minus lambda x2? First we have induced this less than or equal to property, and therefore that continues in this step and that continues in this step, and so therefore we have shown now that f of lambda x1 plus 1 minus lambda x2 is less than or equal to lambda times of fx1 plus 1 minus lambda times of fx2, which is exactly what is the definition of convexity. So therefore positive weighted sum of convex functions is also a convex function. Now the importance of positivity here is that because they are positive, each one of them, each one of fi of lambda x1 plus see, let me explain to you once again this clearly so that you should not miss the important thing. In fact, in the process actually I am probably redoing the whole thing, but it's okay. I don't want you to miss out on how you manipulate inequalities. So now what I am doing here is that to this I am multiplying with w1 some weight, and that because that weight is positive, this thing remains less than or equal to as it was initially, so it remains. If w1 was negative, what would have happened? This would have become greater than or equal to, and if that had become greater than or equal to, then what I am doing right now, which is that similarly, so I will directly put a dot and just write the last one, which is that fp of lambda x1 plus 1 minus lambda x2 is less than or equal to lambda times of fp of x1 up to, I'm sorry, why did I put a dot here? There's just one plus. Unfortunately, you folks are not here to correct me, so I have to be more careful, and so this becomes fp of x of 2. And then what we were doing is we were actually uh, adding all of them. So I multiplied this by WP, and because again the WP is uh, positive number, so the inequality sign doesn't change. And so then when I added all of this, when I added all of this, then this lesser than or equal to sign having been written due to positive weights, I could add all of these together and then group then group this set once and then group this set next, which is what I have done here. And then finally I got it in the form that I need to prove the convexity. Okay, so that proves the C part of it. Now let's take the uh, let's take the D part of it. And remember this linear function again, because I am seeing it here now. I want to mention that this linear function comes in is convex. You should remember it neatly because that's the objective function of linear programming problem. Incidentally, linear function is also concave. Okay, how do you show that it is also concave? Well, C transpose to show uh, to see it is coming at when I expanded it here for linear function, it came at equal to, right? Because it came at equal to, uh, the statement that this is less than or equal to is also valid, and the statement that it is greater than or equal to also valid. When I use the statement that using this equal to, when I use this statement, I get the fact that it is convex. But I could have also said that it is greater than or equal to, in which case effectively I would have stated that it is concave also. So therefore linear function is both convex and concave. Now, vector norms importance, I don't have to explain it to you, right? We have seen that geometry of Rn is very much determined. I mean, in that we needed vector norm a lot, and it's a measure of distance. Earlier we had shown that it is continuous also, and now we have said that it is convex also. So norms has such beautiful properties. If you appreciate it, it's a continuous function, then it's a convex function, and so on. So, and we'll have some more things about good things about norm to say later on. This one you can use. This C property is also very generic. So the advantage of this property is that if you are doing, for example, positive combinations of convex functions, you don't have to worry that you are losing that convexity on the final function. So that's the advantage of this. Now the last one, let me look at the last one. If I is a finite index set, actually in the book there is nothing said like that, but I have restricted it for our discussion to finite index set. So that means 1, 2, 3, 4, maybe 5 or something like that. C is a convex subset of Rn, and fi, the function from C to R, is convex. So function is convex, fine. Each of the for fi is convex. Then the function defined as from minus infinity to plus infinity, defined as h of x. This is the new function which we are defining. And how is h of x defined? Max of fi of x over all I. So that means if you had say 5 functions index set had 5. Suppose index set was, let's say, 1, 2 and 3. Okay, let's say this was the index function. Then h of x would become max of f1 of x plus I'm not sorry, no plus is not there, comma f2 of x, comma f3 of x. So then this h of x would become max of this. If you evaluate it at some let's say, let me not spoil this space here. I'll do it. I'll take a new page and do it here. Do it there. So okay. So we are here. Let me add a page here so that life is easy. We get enough amount of space. So h of x is max of fi of x, where I comes from the index set. So in other words, it is so if there are p such index set has p members, then it is max of f1 of x, comma f2 of x, and so on up to fp of is actually a fp of x. Usually when we say max, we are assuming that the max is there. Otherwise, actually in the Burtsikas, actually they have used supremum, but I just simplified it a bit for our discussion. And so this is what is there. So it's possible that at x1, let's say f3 becomes, you get the max at f3. Maybe at x2 you will get the max at f1. So which function gets picked up depends upon the point, and it is also possible that two of them could be at the max also. Then any one of it you can pick it up, and that value is all that matters. That value is assigned to the h of x. So this is the way we have formulated this h of x. And what this theorem is saying is that this function is actually, if each of the fi is a convex function, if each of fi of x is a convex function, then this function which says evaluate the max of all of them is also convex. Okay, so now how do we go about proving it? So again take x1 and x2. Again take x1 and x2 arbitrary in Rn and in C. Okay, x1 x2 comes from C, the convex set, and then you know that f of I being convex, this is less than or equal to lambda times of fi of x plus 1 minus lambda times of fi of x2. So now we know this. Now we know this, but we can say that each of this individual function is less than h of x. Can I say that each of the fi of x is less than or equal to h of x? Why? Because h of x is defined as max over all of them. So therefore, because it is the max over all of them, each individual one of them is either equal or less. So therefore, I can write this as h of x1 plus 1 minus lambda times of h of x2. Now you take, okay, now you take the max of all of them and look at the corresponding max of this. So other way of saying it, see this side there is no need to put any max because it's only one function which is h of x. Since individually for each one of them is, what I am trying to say is that since individually each one of them, all of them are less than or equal to this, less than or equal to the RHS. So each function, for each function is less than or equal to RHS. So therefore, if I look at max of each of these functions, then obviously max is one of them only. So therefore, max is also less than or equal to RHS. But when I say max, then it is actually the definition of my h function, and so I get h of lambda x1 plus 1 minus lambda x2 is less than or equal to lambda of h of x1 plus 1 minus lambda of h of x of 2. So maybe I'll give you a concrete example to work upon a bit later on, but this proves the 4 properties. Since I assumed here that max is there, but in general we need not assume that a max is there, so better to use a supremum instead. But I just thought that it's easier assuming a max, but everything formally holds if instead of max I replace it with supremum, and that's exactly what has been done in Bert Sika's book. We take a small break here.